have recently had Coulter deal with the other kind of dead mouse in this space. So if you just be careful cleaning up your crumbs and stuff afterwards in order to reduce the attractiveness of mice of all varieties here, that would be great. And let me hand it off to
Good to know.
Kristen.
I am Dr. Kristen, and I organize the Co-Integrate Talk Series, and I'm super happy to this is our final one of the year, but I think we're ending on a really great note. Dr. Kristen Vroom, who is in her first year at MSU, working in appointment in Lyman Briggs and the program in math education, along with Saul Barbosa from program in math education, and Dr. Tenchita Elizondo from Portland State, joining us on Zoom. Thank you. They're going to be talking with us today about their work in thinking about students' engagement in defining and conjecturing. So please welcome these speakers.
Thank you all for being here. It's really such an honor to get to share with you what we've been thinking about for the past year and also previous years and what's to come. So like Kristen said, I'm Kristen Vroom. I'm in Lyman Briggs and Prime. Saul is in Prime, and then Tenchita Alzaga Elizondo, she is at Portland State University. She's currently in a postdoc. They're working on a project that we've worked on together for several years now, and so she'll speak a bit about that project. Today we'll be talking about our past and present and future work to promote students' engagement in defining and conjecturing. And I do want to note before we begin this talk that we're not sharing results per se, but we're really sharing ideas that we have for our task design and our future task design. So for a bit of motivation, I'll start with us talking about this quote that comes from a student who was commenting about their experience in a course that was specifically designed to engage students in defining, conjecturing, and proving. So mathematical practices that allow you to create mathematics. And so the quote says, "You're not being handed a finished package and being told to just take it as is. You're building it. It's the difference between being given an assembled Lego set and building it yourself." And so what I'm asking you all to do is think about this quote. What do you notice about what she said? What do you wonder about her experiences in math courses? And then you'll talk with your neighbor about your noticings and wonderings. And then we're asking at least one person from your group to pull out your phone and use a little QR code so that you can share with the rest of the group some of your noticings and wonderings. So if you'll do that, and then I'll share the actual Padlet where you can post your noticings and wonderings. So turn to talk to your neighbor. What do you notice about what she said? What do you wonder about what she said?
I can pull it up and I'll add things as we
Who's building like this at the moment?
Whatever this is not being like a finished package, right? Like, she asked the lecturers, I don't think they would think of their class in the finished package, right? Yeah. They see it as some sort of evolving story, but like from a student perspective, it's like this is our, like the end is our key actualized. Like there is no deviation. So this is somehow already set up, and you're just like handing it over.
It's interesting thinking about
Sorry.
One of those typical, well, maybe in the student's view, the typical math class where it seems like all the equations, everything is just given to you, and this is how you should do it, instead of like maybe there's a thought process of how we got there, and maybe those things weren't engaging, or they never asked those questions.
And then what would you say about the hardest defining, conjecturing, and considering
Coach?
Well, I wrote something. It was back on club.
I've been waiting for
Yeah.
mathematics to come around to use as a framework to engage with process as opposed to
I
problem.
agree with the things that you said first, both of us.
So we really, I'm really interested to kind of see where we go with that.
It's interesting, the Legos.
It's a very physical, like
Yeah.
tactile metaphor that
Yeah.
But it was the
It
opportunity.
makes me wonder about what experience.
If your group hasn't done so already, I would love to see what you're talking about on the path.
Right?
Because I'm assuming there was some kind of intervention.
it seems like it says commenting about the experience of course designed to
Right. So I was like, oh, that's kind of neat that they're likening that to Legos.
right, yeah.
I like that.
Did y'all post what you noticed or wondered about her experience?
We've added one so far.
I love it.
Yeah, because it's like thinking of the little things like a big set thing instead of it being kind of like, oh, I have a creative thought of my own.
We'll come back together in about 30 seconds.
We have like the
It's interesting.
defining
So
conjecture and
factorization is a whole thing
right,
now.
that could be wrong. Conjecture and so then that act of like
Right, so
pre-assembly building is like you could do something indirectly, right, and have to unbuild or rebuild or something. You know what I mean? Whereas like the idea of a finished package doesn't have room for that sort of like revisionist sort of thought process. That's also true.
Guess I should have done
it's only it's sort of like you're trying
Yeah,
to
if you take a moment and read what other groups were talking about, some of these ideas are resonating with me in my conversations that I've had with Tenchita and Saul. Yeah, I noticed this idea of play with the Legos as well. I thought that was really nice to have an analogy in a math class where you're getting to experience some play. I've also thought about this, what is it, a lot, and I've noticed some, or I've experienced some tensions in like, you know, trying to design tasks where students can be creative and build up school mathematics, but at the same time allowing them to develop the ideas that they have for themselves. I also wondered if her prior experiences had given her the assembled Legos, so to speak. I noticed that in one of those posts as well, or if there was this lack of creativity. And so a lot of our work has been to design tasks to allow students to build mathematics for themselves. And I previously mentioned a bit, but because we aim to use these tasks in whole class settings, most of the time it's school mathematics that we're aiming to support students to build. Though sometimes whenever we have the luxury of time, like in laboratory settings, we can open up for students to be more creative as well, which is really a fun experience, I think, for all of us. So next, Tenchita's not there. Tenchita?
Yes. Zoom looks like it's, oh, she's not.
Maybe she's coming back. Next, I think, Tenchita is going to share some of our work in doing this in the context of Intro to Vroom courses. You there, Tenchita? She looks frozen.
cheerfully frozen.
Yeah. Okay, so I'll try to wing what she had planned to say. We'll see how that works for us. We say past-ish because this project is currently in its no-cost extension year. So this is the Aspire in Math project. This is another QR code that's not our tablet, but it goes to a main page if you want to know more about our project. What we are aiming to do, or what we have currently done, she's back.
Can you hear me?
Yes.
Yes.
Hi. Perfect timing. Can you hear me? We're good?
Yes, we're good.
Okay. Did you say stuff already, Kristen?
I just introduced Aspire and the QR code to go to our website.
Oh, okay. Hi, everyone. Thanks for being patient. All right, I don't know what Kristen already said, but I'll just start over. So a lot of the work that we've done previously, and that builds, or what we are currently working on, builds on the work we've done in this Aspire and Math project, which if you go to that fun little QR code, you can learn a lot about. But in kind of overall, what we're doing with that project is we've created these modular, inquiry-oriented, introduction-approved curricular materials and instructor support materials. And they're modular in the sense that you can pick different contexts that they can be in, like real analysis, which we'll kind of illustrate today, and then also different practices that you might want to emphasize, like proof comprehension and defining. So a big goal of these materials is to support students with this transition to more advanced mathematics, given this intro to proof context. And with that, we've been working with different populations of students, specifically university students with math majors primarily, and then also community college students is kind of this intro to advanced math course. So not necessarily something that's a prerequisite for anything, but just these students, community college students, are kind of at the end of their math at their school and kind of want to be introduced to what more advanced math might look like. Thank you. So as I mentioned, these are inquiry-oriented curricular materials. So what that means is that these are research-based curriculum that is created using design-based research methods. And what we mean by design-based research methods is this iterative process where we start with some idea for a task or a task sequence. We try it out maybe with a pair of students at first and then build up to a larger class, collect some data, analyze to see how that went. How does that match up with our goals for the task? What was going on with student activity? And use that to redesign the task and try again until we kind of continue this cycle until we're happy with one form of the task. And this redesign is often guided by the instructional design theory of realistic mathematics education, which I'll talk a little bit about in a bit. But overall, overall, inquiry-oriented instruction is it's part of a bigger thing called inquiry-based mathematics education, which Larson and Rasmussen have identified these 4 big pillars that kind of help frame what these classes are about and what you can kind of find in them. So the first of these are deep engagement in mathematical tasks. So this gets at this idea that students are really engaging with the math concepts with these tasks. Then there's instructors inquire into student thinking, which is a really critical part of these inquiry classes, and it describes the really important role of the instructor, that they have a really active role to support this student-driven course by inquiring and leveraging student thinking to kind of move the mathematics forward. Then there's collaboratively processing mathematical ideas, which is just that we want students to be working together, perhaps in small groups, in pairs, or just as a whole classroom community, to really be working on the mathematics and building that mathematics collectively. And then lastly, this really critical idea of the instructors need to foster equity in both the design and the facilitation of the course. So both preparing to set up the structure for the course that creates a more inclusive and equitable environment, but then also being in the moment and being aware of how to facilitate a class to support more equitable participation. Next slide, thank you. So as I mentioned, we use the theory of realistic mathematics education to guide our task design. So realistic mathematics education at its core frames mathematics as this human activity and has several design heuristics that support this design of the curriculum, but I want to highlight one of them today, and that's guided reinvention, since it's been a big influence in our work. So guided reinvention communicates this idea that students should be guided, and primarily by the instructor, to create mathematics from more informal ideas, and supports this idea of progressive mathematizing, which is where really students' informal ideas are getting organized and are getting built on to develop this working with is both accessible and meaningful to them. And there's different ways that us as designers can create these kind of contexts, and one of them is using historical examinations to look at how in history was this mathematics kind of first confronted, how did mathematicians first confront this problem, and then also looking at students' informal solution strategies. So what are students actually doing when they're working through these tasks? So to illustrate those ideas, next slide please. I want to walk you guys through one of our big motivational tasks that we have for the real analysis module. So with this task, we start off by supporting students to conjecture that every odd degree polynomial will have at least one real root. And this supports the students generalizing that a little bit to come up with a conjecture that reflects the intermediate value theorem, so that any continuous function with a positive and a negative value must have at least one real root. Then, in order to kind of get the students thinking about how might we find this real root, we have students reinvent a method for approximating a root. And a common one that we have is what we call the bisection method. And then students play around with this bisection method and notice concepts related to sequences and some properties due to this approximation method. So, I'm going to walk us through kind of what this approximation method looks like. So, we start off by, next slide please, having two values, an A1 and a B1, that represents, there are two inputs that map to opposite sides. So if you notice here, our A1 maps to a negative value in our function, and B1 maps to a positive value. Then what we want to do is find the midpoint of that interval. And we ask ourselves, okay, does this input map to a positive or a negative value? In this case, it maps to a negative value. So this now midpoint is what we identify as our A2. So it's our now new negative value, negative endpoint. And then since B was still positive, since the midpoint was negative, we just label B2 as our B1. So they stay the same. So then we again ask ourselves, let's find the midpoint. Does this midpoint map to a positive or negative value? Again, in this case, it maps to a negative value. So now it's our new A3. And then B3 just stays the same. And then if you notice, at each moment, we're kind of narrowing down our interval to kind of narrow down where our root might be. So we again want to ask ourselves at this point, what's our midpoint? Is it positive or negative? In this case, now we have a positive output, so now that becomes our new B, and our A4 stays the same. So in general, we're really narrowing this interval down, kind of getting this smaller smaller area where root approximation might be. So what I want to do now is ask you guys a question that we ask our students. Imagine if we continue this bisection method forever, going on and on this kind of cutting in half and figuring out if it's positive or negative. What do you notice about the ANs that we have here, and what do you notice about the BNs? So I want you guys to take a minute with your groups or whatever you are. I can't see you, so I don't know what your setup is. But to think about this, and also write down some of your ideas in the same Padlet that you guys were working on before. So, have fun.
Okay. Well, the A's move right and the B's move left. It's probably important.
I need to go through the slides again to show how it works. Experience the situation.
Good.
Whatever
people want.
For those of you who want to see it again, this is how the student's bisection method works. So they start with two input values that map to opposite signs. They look for the midpoint, and then they kind of narrow it in. So imagine doing this process forever, taking the midpoint between the AN and the BN, considering the sign of the output. What do you notice about the ANs and the BNs? You have to continue this forever.
Goes through the iteration.
And especially there's gotta be ways.
Not quite sure what I'm supposed to notice, right there.
Oh,
So that if you could
Convert.
play that and play where
Yeah.
the slides go.
yeah, I'm pretty sure you can put an iterative formula within coordinates. So you might just have to do it at like x value comma 0. But then you could define it based on I and then just have a function. And I think it would actually endpoints. 2 or 3. This is making me realize I haven't used it in a long time.
Right, in my head, I'm like, okay, can we do a better algorithm to make it converge faster, right? It's sort of what
I think that would also help to see that motion, because I think that's one of the key intuitions, is the idea that the x values that are the endpoints have to get smaller, so the interval has to get smaller.
That would be the shift.
I guess now I'm shifting into math, like how long is it going to take to converge? That's probably probably not a question that
the idea of like our
students.
like that approximating is really finding an interval, right? Until you find an interval that is within 0.
Right.
So like maybe like connecting the numbers by approximation, like your starting approximation is the whole interval
Right.
possible.
Yeah.
Let me try
And I guess this is a good one because it's relatively, it's a good like initial example too, because it's easy to see that it's got to converge. Because you're always taking
infinity and show them they're different again.
Yeah, you're always having
To show that there's nothing outside bounds.
I could see this being a good one for students as an example early in the class, or later in the class.
Not typing.
They could argue through it even if it's informal.
I'm going to revoice some of the ideas that I've heard as I was eavesdropping on your conversations. I heard some ideas that the ANs were getting closer to the root, or some people said converging to the root. Same thing with the BNs. The BNs were also getting closer to the root, so it was converging to the root. Another idea that is common that shows up in our courses is that the ANs are always getting bigger, and all the ANs are like less than a B, any of the B terms. All the BNs are getting smaller, and they're bigger than all the ANs. So some of those are some informal ideas that have come out today and have come out in our courses.
Thanks, Kristen. Yeah, so similar, I said, like what I was seeing also, what you guys wrote in the Padlet, are very similar ideas to what we get with our students. And as I kind of noticed from just listening, a new challenge to moderate a discussion when you can't see or really hear anybody, is there's so many different things you can look at, right? And there's so many different things that you can notice with this activity. So to just kind of summarize, this bisection method activity, we chose it as kind of this big motivational activity since we see it as being experientially real for our undergraduate students because it's accessible. These students have prior experience with polynomials and finding roots, so they kind of have this access point that they can start off just thinking about what is happening with the activity. And then also it's rooted in a historical context. So this approximation method is actually motivated by Cauchy, a famous mathematician. His strategy for proving the intermediate value theorem, he leveraged approximation methods to come up with a lot of the techniques in his proof. So we wanted to draw on some similar ideas for our students. So as you guys noticed, this activity also invokes a lot of informal ideas from our students about sequences, different properties of sequences, like increasing sequences, bounded sequences, converging sequences, which are all things that we kind of use to motivate how we move forward with the class. And these are things that we explore throughout the term with all of our materials. So as we're kind of wrapping up our project, we started to wonder kind of how can we support students to engage in this creative activity earlier in the college experience. Because as you might have noticed, our curriculum materials really engage students in creating their own mathematics and conjecturing, and we engage them in defining, and we have a lot of creative work that we see as really, really valuable for students. So we want to know how can we perhaps get that for students earlier on that maybe haven't picked a major yet, and just kind of introduce them to what mathematics could really be earlier in their study. So that's what Saul is going to talk to you guys about now.
Hi, thank you, Tenchita. Yeah, so I'll be talking about what it is that we've been going over this semester. So this semester we've been conducting an experiment with 2 students, Stella and Lara, with the goal of expanding the Aspire materials that Tenchita just brought up, but for a Calculus 2 kind of course. And so the way we're collecting some of this data is using a Miro collaborative online whiteboard, which is super cool, fantastic. You can use it on multiple devices, collaborate with like 100 or 1,000 people, depending on what kind of plan you have. We get a free educational plan, by the way, if you want to look into that. And thank you, Brady, by the way, for introducing us to Miro. It's been super helpful, so we really appreciate it. So Stella and Laura have been working with us, and one of the first things that we did with them was running through this bisection method idea. But something else that we were doing was we were keeping track of some of these values, such as A sub n and B sub n, as we were finding out approximations for those roots. Another one of the values that we were keeping track of were the C sub n's, which would be the midpoints that we were getting between A sub n and B sub n. So from those, we were creating this table of values to keep track of. So you'll notice that this table only goes up to 6 steps. So something that Stella and Laura were wondering was, what if we were to keep on going, right? What's going to happen if we go on like an infinite amount of steps, at which point they were introduced to the idea of sequences kind of as infinite lists that we can list out over and over again. But we also had other representations that were introduced to them, such as one-dimensional lines, other tables, or two-dimensional graphs, where you have the n-axis, and on the vertical axis, you put in your values for, say, A sub n or B sub n, so on and so forth. So Stella and Laura were asked to convert this table into some of the graphs that you're seeing right now. And from converting them into the graphs, they started noticing a couple of properties of sequences that we tend to notice, such as increasing and decreasing sequences, bounded above, bounded below, and converging sequences. Of course, they use their own terminologies. For example, for bounded above, they wrote that this is always below the x-axis, so we're bounded above by 0. So those are some of the properties that they were noticing. So then we also asked them, well, hey, can we generate some more examples that are maybe somehow a little bit different than the sequences that we've been working with so far? So Laura had brought up this idea of half-lives. So I don't know how many STEM people are on the room right now. I'm guessing a lot of us. But the idea of half-life is that you start off with a substance, and at a particular unit of time, that substance has been reduced by 50%. In the next unit of time, that's another 50% reduction, so on and so forth, until, as they say, you have functionally no amount of substance left. But they also recognize that you still have some, but also none. It's a really fun thing. So cool, that was a fun one. Another fun one that they had brought up was the idea of sine and cosine, because they were, again, thinking about trying to come up with sequences that were somehow different than what it is that we've been working with. They noticed, well, hey, sine and cosine are oscillating. That's a pretty cool property to kind of think about. But they were thinking about it in terms of the domain being real numbers. So that makes things tricky in the sense of how can we make that a sequence, because, for example, one of the representations would be to be able to list out some of the numbers. So how could we list out some of those values in said sequence for, say, sine or cosine? So this was, kind of considered a non-example in that case of a sequence. So later on, eventually, we were talking about, okay, well, what if we were to define a sequence? So to help them define a sequence, Laura and Stella were prompted to create a definition with a property that made sure that examples, that was true for examples of sequences and false for non-examples of sequences. So these two up on top are the initial drafts that they had. So a sequence is a continuous list that follows a certain mathematical relationship through all values of x. And a sequence A sub n is an infinite list of numbers that follows some trend that can be modeled by a function. So Stella and Laura noticed that, okay, we have some similarities, we have some differences. So they combined, I wouldn't say combine, I guess that's not necessarily the term, but they worked out so that we would have one agreed upon definition for a sequence, that being that a sequence, a event, is a list of only natural numbers as inputs where there is always an output and the relationship can be defined as some mathematical function. So that was the definition that they came up with. Eventually, they also worked out new examples for sequences. They worked out so many. What you will see on your table is that you have some examples of sequences that they came up with. They're the tiny little rectangles that are in the paper clip. Feel free to check those out. As they were working with these examples, they were sorting them based on some of the informal ideas that they were coming up with, such as sorting them based on increasing or boundedness or convergence. What we have right here, and some of y'all also have them on the table, is we have one of the maps that they were using. This one is the boundedness map that they were using. You'll notice that we have a green bubble for bounded below, a blue one or purple one for bounded above, the intersection of those, and a red one for unbounded above and unbounded below. So the students went ahead and sorted their examples based on their descriptions and understanding of what it meant to be bounded. So that's an activity for y'all to do for about 5 minutes. Go ahead and, with your group, go ahead and sort out where it is that you would put these examples based on some of their descriptions.
Examples real analysis because knowledge to know that it's not that bad. But also I wish that I would have done something more in line with this in the class.
Hang out with y'all for a bit.
Start with the easier one here.
Yeah, good one, good.
Right.
Did you suggest the categories or did they come to the categories?
I had suggested examples of bounded above and not applicable, and then they decided that they would like to also include bounded below. So at first we had those categories, and we realized that they weren't mutually exclusive. So I suggested this afterwards.
Yeah, that's a neat move that they made too, to combine them since it's so crucial.
It was definitely, that we did it together.
Yeah, it's not asymptotic, is it? Asymptotic?
Oh, well, usually my guess would be this one. You take this.
Yeah.
Right, like,
Bounded by zero,
right?
Yeah.
That's a function
Yeah.
you're familiar with. And
Right.
then you say, right, this is clearly unbounded above and below.
Right.
So then, how would you turn this?
Yeah, so as they were going through this, they were asking.
What's the fancy term for the things that are bounded by a function above and below? Doesn't that have a nice name? Maybe I don't want to remember that.
I know.
I just couldn't help but think of it.
I hope this is not intimidating.
Yeah, right, and then that's not.
I love that word, when you
Yeah.
right, because the tendency is to think.
Yeah, totally. That's something that we explore.
But then you're like, well, like, that brings up questions of like domain, which I know they don't. You know what I mean? Like you have to evaluate.
That's what I was thinking on the definitions.
Yeah.
Is I wonder, and I actually would ask this at one point. I was kind of surprised they went to function so fast. With Calc 2 students,
Yeah, that was
doesn't
a
usually.
Hopefully we'll get there, maybe they update, I'm
I mean,
not
I've
sure,
worked
I
with
think
like
this is.
linear algebra students that don't see, and differential equation students that don't think of sequences as related to functions at all, because of the different domain.
Because the ones who have continuous even in her.
Yeah,
That was
I was kind of
interesting.
impressed with the initial definition, so that made me wonder. But I wonder if charting them like this, which is kind of rare,
Yeah.
makes that connection a lot clearer than it often is in textbooks. Honestly, do they even put pictures like this in textbooks? I'm trying to think. I don't think it's that common,
No.
which is a
You don't think
shame.
of sequences as
Founded by hand.
No,
Right.
not at all.
And this has always been my move to make it make sense too, because once you see
We'll
it's
be
just a
coming back
function,
around it for
Yeah,
about 30
it doesn't
seconds.
specific
feel
image.
abstract.
So,
Yeah.
Right.
you might wanna-
because then you can use all the things you know before and you can visualize.
It's a mirror image.
I don't remember that.
A plus.
Is it your A and B? I don't know.
Oh, that
There's this like the
These
We're
days,
not grading.
Okay, yeah. So that's probably the idea.
There you go. There you go.
graphically.
My grade is bounded below.
This is a good one too because one example.
Yeah, there you go.
That's something that we talk about a lot, is
Yeah.
if they're correct, and we're like, well, we're not talking about this is correct, we're making these decisions. So that's been kind of
Go see the kind of things that, oh, should I have? This felt very inaccessible, even in Calc 2 as well.
Okay, so just so y'all know, it's all good if we have different maps. That's very important to note. But this is how Laura and Stella had done their sorting of their examples, which again, this is based on their particular understanding and description of bounded above, in which we all might have different ones, and that's all good. So if we have different ones, that's fine. We're not grading y'all, no problem. we don't have to worry too much. But something else that happened while Laura and Stella were working through this is, sorry, that was, oh, that's also, there we go. Okay. Is that Laura and Stella were also coming up with questions and conjectures. So for example, Stella at some point had conjectured increasing means unbounded above. Now earlier they had already defined increasing for themselves. They had said that a sequence is increasing if all of the points must have a higher value than the previous input value. We interpret that as a sequence is increasing if all of the outputs must have a higher value than the outputs of the previous input value, which is kind of consistent with the Stewart's calculus textbook, which London Briggs uses, and I think some other MSc courses use Stewart, and some people also call this strictly increasing. But in order to explore the conjecture that Stella had brought up, we asked Stella and Laura to draw a new bubble within their boundedness map, and this bubble would contain increasing functions. So a new activity for y'all to do is kind of think about where in your map would you include a new bubble for increasing sequences. Where would you go ahead and put that in there? So think about that a few minutes and we'll come back.
Strictly increasing functions.
well,
I'm gonna go.
so increasing could be bounded below. Increasing could be bounded above. Increasing could be unbounded. So it's gotta be one of these over here, right?
For conjecture, increasing means unbounded above, right? So then your thought is that if you were increasing, it would live outside of this rectangle,
I
right?
don't think you would.
But then immediately
Yeah,
you
because
run
you're
into
bounded by the first value.
That,
this function
yeah.
right here.
In your sequence.
Increasing over
So that equals the bounded. Oh, you see our
I like that. Oh, yeah. There aren't any examples of
Is it,
increasing
But isn't
not every
this
number increases.
This one's strictly
That's a
increasing
good-
as well. And
It's a
it
really
is also bounded
good initial definition.
below and above.
or,
You're
in
just
other words,
increasing
does this have to
all
encompass
staying
all the values?
We need something that has like a sign dampening factor on it that increases otherwise.
Because, but then it's like when you look at the graphs where there's points of increasing and decreasing, are we talking about strictly increasing?
And there's some strictly
Or,
increasing. Okay, so here's the question.
So their understanding of increasing is strictly
okay,
increasing.
then, yeah.
What most, what a lot of people would call it strictly.
Okay, yeah.
No, because this one is a good example. It's bounded above by 0, but it's really easy. Increase pressing up against 0.
Bounded.
too?
Yeah.
Yeah.
Alright, so this is where Laura and Stella had put their bubble for increasing based on what they define to be increasing, based on what they define to be bounded above and bounded below. This is where they ended up deciding to put it. And a nice thing about where they decide to go ahead and put in their bubble is that through this mapping, they're able to now come up with counterexamples for statements that would be considered false under their understanding of these properties, such as all increasing sequences are unbounded and all unbounded above sequences are increasing. So this could help them out in separating the idea of increasing and unbounded above. But at the same time, the map is also helping in bringing out some conjectures, such as that all increasing sequences are bounded below. So hopefully as well, this motivates the idea of justifying some of these conjectures and maybe even defining some of the things that haven't been defined yet, such as bounded below, bounded above. So that's hopefully what we get to see. Throughout the rest of the semester, we're going to continue working with Stella and Laura in supporting them to define conjecture and justify about sequences. Hopefully, we want to move on to supporting them to do the same, but for series, which we're viewing as sequences of partial sums. This right here is an anticipated sorting that we think we might be seeing based on what we've seen so far about sequences for series convergence. So hopefully they'll start to also conjecture about series convergence and series divergence. So that's kind of the plan for this semester. I'll now pass it on to Kristen so she can mention what's next for this project.
Awesome. Thank you, Saul, and thank you all for joining us and exploring some of their ideas and our own ideas about these sequences. So in looking ahead, we have two directions that we want to explore. So first, in thinking about scaling up our tasks to the whole class setting, we would like to redesign the tasks themselves to optimize for equitable participation. And then secondly, in thinking about designing more tasks for like the calculus sequence, we would like to find motivational science context that elicit informal ideas about mathematical ideas that are typically covered in Lyman Briggs courses. And so I'm going to share with you a little bit of motivation for why those are the two directions that we want to go in, and then we'll open it up for some more small group discussion. So first, if we go back maybe 10 or so years ago, we would find that many of us would assume that inquiry-based instruction was a more equitable experience for students. However, more recently, we've found that this isn't necessarily the case. And this makes sense to me. The more we allow students to guide the mathematics in the classroom, the more likely we are to see power differences from society show up in our classrooms. So for instance, Estrella Johnson and some of her colleagues found that in inquiry-oriented abstract algebra courses, men outperformed women in learning gains, and this was not a difference that was detected in non-IO courses. And so you can see that in this graph here. The bar graph that's in white represents the women, the shaded graph represents the men. This difference is scores on a post-exam from after the course. And so you can see there's a significant difference in the women's performance than the men's, and that's in comparison to courses that weren't using that IO materials. Other researchers have documented that student discourse in inquiry-based settings in which students are marginalized identities in mathematics were excluded, experienced explicit microaggressions, or given fewer opportunities to develop positive mathematical identities. And so our big lesson here is that inequities can be amplified in inquiry-based classes if there's no intentional ways to mitigate for them. And so we are trying to mitigate for them with our task design. And so we plan to adapt the tasks themselves so that we optimize for students' equitable participation, where we're drawing on Reinhold's and their colleagues' conceptualization of equitable participation, being that students with marginalized identities in mathematics receive at least a proportional share of opportunities to contribute to the task. So we are planning to do this by incorporating ideas from complex instruction. So for instance, building in meaningful group roles into the task design, as well as incorporating revision structures into the task to support a culture of rough draft thinking. So for instance, building in think, pair, share wording into the tasks themselves. We have this caveat that we don't think this is actually going to solve the problem. Instructors' role is huge in actually implementing the task, and we have a lot to learn from instructors on how they can implement the task. But from this perspective, we're trying to set up the instructors for success as much as possible through the task design. And then secondly, in thinking about Lyman-Briggs students' interest, who come to college who are interested in science, we want to design an initial task like the bisection method situated in science phenomena. So one of the plenary speakers at the Vroom conference this year was Kristen, who's at North Dakota State University. He does some really cool interdisciplinary work at the undergraduate level. One of his main points in his talk was that designing genuine interdisciplinary research projects and tasks is non-trivial. And jokingly, but rather convincingly throughout the talk, he made the point that mathematicians are bad at writing physics problems. And I'm pretty sure he would agree that mathematicians are bad at writing biology or chemistry or what other kind of science problems. And so we are currently looking for collaborators to support us in this endeavor. And particularly, we are looking for folks who could help us design motivational science tasks that would be experientially real for students and elicit informal ideas about mathematics that we cover in the calculus sequence in Lyman-Briggs. So starting from pre-calc, we call it functions and trig, all the way up to calculus. And so we are hoping to learn from you. And so what we have planned next is to turn and talk to your neighbor about whichever future direction you're most interested in. And we have a couple of guiding questions if you want that to support your conversation. We would love you to use the Padlet so that we could see what you all talked about, as well as other people in the room have talked about. And then maybe 5 minutes to go, we'll come back and we'll answer any questions that you might have for us in our projects that we've been talking about today. So if you'll turn and talk to your neighbor, what experiences you have in these sorts of areas?
There you go.
So I have introductory students sitting in small groups of like 3 or 4.
Well, the first one I was looking at was whether or not that was actually a significant difference or meaningful
So they sit on the table and not for like pedagogical reasons, but for reasons that was how many markers Taylor gave me when I asked in the office. I gave like 2 markers and an eraser to each group. And there's 4 students in the group. So like sometimes it was one student who would pick up the marker and then they always left me a marker in some of the groups. Because then I would write something. But also sometimes that was like everybody did not have a marker. So sometimes it was very explicit, like I would hand you the marker and I'd say, okay Val, you drive.
Yeah.
What is this group?
Right.
So like what would it be better for every student to have a marker?
And these are tasks that they work together with?
They're like proof problems that they work on in groups.
How did you decide who got the marker to begin with? I think I missed that.
I would just pass out the markers and erasers on the table, so whoever picked up the marker first. But then if I was coming over and talking to a group, I would usually write something, and and then if
That's
there's
right.
someone I really did want to
It's
say
good that
something,
you're getting the
okay,
engagement, right?
I sit
Fully
down and like
engaged in the
explicitly say
process,
to do
right?
that.
So that, those
Right.
One of the strategies that I've used is actually to go from having
That's
initially enough markers for everybody
the,
to just purposely handing out one per group and making it so
yeah,
that
cool. Give me a,
either there's an assigned
give
role,
me
somebody's the writer, because then it requires everybody to communicate more than just the one person's writing. And usually I'm purposely choosing the person, so it's not the person who writes a bunch already. So I've gone the opposite direction now, purposefully, and it takes a while for students to get used to it, for sure. But I've had positive outcomes with that in the past. Because I do think that having everybody with the marker can be problematic too, because a lot of people just have the marker but not use it because the other person's writing so much. And a lot of the time it's one person writing without doing the rest of the collaboration, in my experience, without a lot of like training, I guess is a good way to call it. Like very explicit prompting for like, you drive, like you would put it.
It's interesting how much that task changes if you just handed them a piece of paper, like one group lab or whatever instead, right? It's like, I mean, then you can't control the writing instruments, but then like, but there's some sort of assumption that that's a permanent impression now, or is it feel like a whiteboard, like ephemeral in some way, right?
No,
Like
agreed.
they're just gonna erase it and like take their own notes on it and then move on.
No, that's
So I like the whiteboard a lot because it does remove that pressure of like, what's flex.
Right. Yeah.
Right.
So,
Most of the math classes that I've taught, I've had the pleasure of being in a room that just has either blackboards or whiteboards around the whole room. It really does help, I think.
so much nicer. I was at one of the
That's an interesting one, right?
they had a classroom that had whiteboard tables at it.
Yeah, I had those too.
I like
those
the
too.
STEM building, yeah.
They're
Those are
nice.
amazing.
Not our crusty ass.
I know.
Yeah, I was gonna say it's a little bit. Which I was going to classroom stairs.
Well, I did one of my classes I moved into, they had me in like the conference room of the criminal justice department. It was there's not enough seats for all the students.
Oh my gosh.
So we were like, okay, like we can't teach here, please find a exhibit marker. So we're over in the active learning room case. Those are really nice.
It's interesting because the buildings to the room that they moved us to in the STEM building, like the setup is terrible for my students. It's like
That's a good one, right? That's a good domain, right? You know?
Can you move them?
I can, so I want to move them into basically these funky looking groups now. Because they learn the projectors on the right. And of course, students sit all the way over here, and I'm like, how do you even see anything that I'm teaching? And not just that, we have these big whiteboards that are just sitting in a corner. So I'm like, I wonder if there's a way I can kind of implement them but without them being like a full-on distraction.
Well, my suggestion would be just get students used to at the beginning of every class when somebody from the group grabs the whiteboard and brings it up to their table. That's what I would do, because you don't have the time. Or like you said, it would be a distraction if you were the one doing all of it.
Yeah.
But if you just make it part of a like, all right, get ready, somebody grabs the handout, somebody gets your, like, rolls over a whiteboard. At the end of class too, if you needed to move them back for the
Yeah,
next
for sure.
because that would make it doable.
Yeah.
Just moving the tables, like if you get there early, they're gonna stand up and help you. Like,
Yeah.
That's how I usually start. I start doing it, and the student jumps in, and then like the next time it's mostly the students. And I'm like, all right, grab the whiteboards.
so I was teaching I was in Berkeley last semester, but Saul really comes to observe my class. And originally the tables were in like rows, and I had put them together. That room was like not very used, so I just assumed that whoever was after was just leaving them there. And then Saul got there early. He was like to observe my class, and he was like, no, one of your students comes and puts them together.
Oh,
You mentioned that in class
Yeah, I
last
remember you
semester.
said that.
That
That's
is-
so cute. Yeah, I think I'm gonna, especially now since they're doing the unit exam, like we're in a new unit, so
New classroom.
Yeah.
I was gonna say, I mean, going back to some of these things, like a lot of those things are the prerequisite. How would you do a lot of this before you first are able to create a room? And then, like you're saying, just actually various things. There's a lot of factors that contribute to unlock that.
Because that's a big mid-semester change from like this nice where I can move around to all these rows and people in the back corner far away and I can't even reach them. So
Alright, we have about 5 minutes left, so we're gonna open it up for questions. If you have them, me, Tenchita, and Saul can potentially respond to them. I don't know, we'll have a conversation with you. Yeah, Kristen?
So one thing, a burning question I've had for the last few minutes is when we were doing the sorting task and stuff, one thing that I noticed is that we were informally engaging in conjecturing and justifying as we were sorting. And so, yeah, like, I don't think you were implying this, but do you find that with a lot of these tasks, there can be that kind of, not cyclical nature of it, but it's like they sometimes will do all three things in the same sort of activity, even though you're not explicitly asking them to produce a conjecture to justify it.
That's something that I've personally been working on as the designer of task. So previously, a lot of my tasks is like, okay, we're gonna sort examples and then we're gonna write the definition. But I wanted to, this time around, I wanted the need to come more from the student rather than me being like, okay, now's the time that you need to write the formal definition. And so I've tried to allow this non-linear approach to developing the ideas. So for instance, we haven't defined unbounded above or bounded above yet. And I'm thinking that it seems as though that some of the conjectures that they are making, in order for them to be convinced that they're true, they need more, a better way to articulate what they mean by it in order to make convince for themselves that it's true. That's my hope. I'm not sure if it's going to work out, but that's where we're at so
And
far.
it's really neat because I think sometimes students come away with, because I'm, you know, my realm is secondary, they come away with experiences with geometric proof, not really understanding how important the definitions are that they're using. It just, I think this really brings that to life. So.
Thank you. AJ and then Nahimia.
So related to that, with that sequence task, I was curious about conversations in the class or by students around, like, is there a starting value to a sequence, or is it part of a, you know, a subset of a larger sequence and they continue on in both directions, or can you say a little bit about that?
Yeah,
treatment?
yeah. So we, maybe Saul, you feel free to pitch in as well. We started the idea of sequences really based on that bisection method, where there was an initial starting point. There was a first step that we were talking about in order to build it. And so through negotiations with the students, we've come into an agreement that there's a first number and the list goes on forever. Because that's how it shows up in the initial context that they were put in order to start thinking about sequences. Did I answer your question?
Yeah, because in the sorting activity, you kind of open it up even more, right? And so the mathematical functions, you're not saying from this, you don't identify a starting value for that. We just see the points on paper. So
Yeah, something that
open.
it is open, and that's something that we continue to come back at. If you think about these sequences with the real numbers as the domain, you would likely sort it differently, and that's been a conversation that we've had a lot. They'll respond to like, oh, this is bounded because of natural numbers, meaning because there's a natural number, there has to be a first point that we're dealing with. So that's a conversation that's been really fun to explore with the students. Inia?
Yeah, so two things that really caught my attention. So in one of the bubbles that you showed on your slides, I read something like instructors are inquiring into student thinking. And the other, I think it's a beautiful idea that one of the students shared. So I'm kind of like connecting those two ideas, and my question is, what counts in this project? What counts as student thinking? And then when I think Saul was sharing that
question, but I am going to mention that we do experience like some tensions whenever we're working with the students. Like we want to stay true to the student's idea, and then there's a real tension that we experience where we want them to leave our class or leave our teaching experiment and be successful in the class where they're learning about sequences. And so we experience this tension that, yes, we want to draw on their thinking, and we also want to use that thinking to build towards more conventional ways and that we talk about sequences, for instance. And so that's a really hard thing to do, to try to stay true to both. I feel like it's a very fine line that we've been walking. Saul, did you want to add?
Yeah,
Maybe actually
like
answer
I mean,
his
they've
question.
thought about increasing in different ways as well, not just in this strictly increasing way. For example, one cool way that they brought up increasing was by a trend. You know, like vibes, you know, it looks like it's going up. Even if we have some dips that go down, they would still sometimes they had considered a sequence to be increasing if, in general, if you could like, you know, draw a line of best fit. If that was a positive slope, that would have been considered an increasing sequence anyway. So there was, I don't want to say compromise, but there's also some, you know, the fact that we are working with two people and not just one kind of also makes it tricky on deciding where do we want to go. And at the end of the day, we are choosing something so that we can move on from there, but we are honoring what they choose and building on that as, okay, so this is what you want to be increasing, we'll go with that as increasing and we'll follow along from there and we'll see what happens.
So, for instance, they had this like holistic idea of increasing, and so we're still honoring the holistic increasing, and we're also talking about the Stewart increasing, how others have chosen to sort their sequences. I'm not saying that one sorting is a right or wrong way, but it is a choice that we make, and so I find it's really fun to like think about, well, what are the implications of those choices?
So, I'm sorry, this only goes until 1 o'clock, so I just want to briefly close and just say thank you to Create for STEM and the program in math education for again hosting Co-Integrate this year. Thank you all for coming. Please stick around to ask questions of the presenters. You don't have to like leave or anything. I would encourage you to stick around and chat. Also, I guess I'll make a plug. Prime is having an open house in Wells Hall. There's like appetizers and desserts, right, Lisa?
Yes.
Yeah. So come on over and see the new space. Yeah. All right. Thank you so much.
Thank you.
Where's it at in Wells?
C-109, Wells Hall.
C-109.
So big, tall part of the building, first floor.
First floor. That's right.
Thank you all for coming. Saul and I will stick around for a little bit.
Thank you.
Yeah. Oh yeah, because you don't have your phone. Yeah.
Two. About to go set it up.
And I said in my email, see you around. I didn't expect you to see you around the next day. Sorry about that. But thanks again for the info.
Yeah.
It's really helpful. It's nice to see you too.
Yeah.
It's been a bit.
I know, it's been a while.
It's so funny because you're probably just like right above me in the math building. But it's so easy to just go out the door and not see anybody else. Sorry.
Oh, sorry.
I hope I wasn't blocking. I realized I was coming over here to say hi, and then I plopped right in front of me. Hopefully I wasn't blocking the view.
You good?
If I would have had more time, I would have adjusted over the side. But
Hey,
good to see you, though.
did you figure out some of that three-part structure that I would think about in your dissertation?
Yeah, so 2 of the studies are ones that I had decided to move forward in the proposed proposal, and then one is more of a theoretical combo of some of the other stuff that I've been thinking about anyway, that is related and allows me to write the thing that I want to do. And I already had a draft of it, and I was like, oh, I should just elevate that. So, yeah. How about you? How's your efforts been going?
Yeah, it's good. You know, Monday's my proposal defense.
Oh.
Yeah, but it's kind of like a fantasy thing, which I did a lot. And it's for that class that I mentioned before.
Okay.
Yeah, so it's the class is still going on. Wraps up in April. Yeah, it's going. I mean, it's starting because we're asked. The first really just happened in the fall. It's 3 credits in the fall. But the continued expectations of working straight. Additional work. And that doesn't even count as a course, really. We're really just relying on the